So, we have been discussing the London equation, which is one of the first major developments in the theory of superconductivity, trying to explain the phenomena that happen in a superconductor. And one of the most important phenomenon that happens is Meissner effect. Okay. So, London and London, this F and H London, two brothers, they understood that the superconductivity can be broken down into two parts, which is one part of the conduction electrons are superconducting and the other part is normal. And the normal part and superconducting part, they are in parallel, and therefore, the resistivity is shunted by the superconducting component, and therefore, you will still see 0 resistivity, although the other part remains dissipative. Typically, these measurements are done in 4 probe geometry. So, it is just as an aside that if you have a superconductor, you would suppose you do this kind of a measurement, 2 probe measurement, then of course, there are this you measure the voltage here and you send a current through this, and then you are measuring the voltage includes the contact voltages, contact resistance and all that. So, that needs to be avoided. So, these contacts are they have to be avoided, and ideally one does a 4 probe measurement, which is just this. Instead of measuring the current and voltage at the same lead, one measures current and voltage at 2 different places leads. Okay. So, and you find out the voltage drop across these 2 leads, and then you know the current that is flowing, and so you know the resistance between the 2 leads. So, that is the standard method of calculating of measuring low resistances and very low resistances and so on. So, so that the contact resistance does not come into picture. Okay. So, this is just an aside. We are starting to do this again. Let me just show you what we did. This is London equation, and this is not London equation. This is the equation from Drude, right, for transport, with the caveat that tau goes to infinity. Okay. So, this 1 by tau term, which was there in Drude equation, can be safely dropped, and you can have a just like a Newton. This is a Newton's law basically. So, for the supercurrents, this is the equation of motion, and then you write J equal to minus NEV, NSEV, V sub S also. This S means superconducting part component, and then of course, what we did is that we used we just took a multiplied by this equation by EV, NEV, NE, and that is what we got. So, NE square by M on the right. So, this is what we have just done. Then one uses the Faraday's law, which is this, and combines it with this. So, what one does is that one takes a curl. So, this equation, for example, d dt of J equal to NS E square by M into E, you take a curl on both sides. And then curl of E from Faraday's law is equal to 1 by C del B del T, and put it back in. So, that is, so you will get time derivative on both sides. So, you can combine the two on one side and write del del T of curl of J plus NS E square by MC into B equal to 0. and this means that this whatever is inside the bracket is time independent, it is a constant in time. Now, out of all the possible constants that you can choose any combination of constants. There are large number of constants you can choose, I mean infinite in principle. So, you choose the one which is just 0. So, this object is 0, is what London chose, and this is called the London equation. So, this is London equation. So, it is actually 2 Londons. So, London's equation you could write as well, but anyway this is historically called London's equation, London equation. So, that is about it that we did, and then we sort of connected that London equation with a theorem by Bloch, which said that the overall momentum, average momentum in a superconductor must in the ground state must be 0. So, P plus E A by C equal to 0. So, this was Bloch's assertion that in the ground state this is what will happen, and that is so the ground state will carry no net momentum, and that is what this is, and this is actually consistent with what London had written down. So, that is what we showed. The consequences of London equation of course are dramatic in the sense that it is that equation which showed that there indeed is a Meissner effect in a system. So, how does one do that? Let me just show it. So, from London equation we get curl of J equal to minus ns E square by m c into b, right. Okay. Now, of course, there is another equation that 4 pi by c into j, which is Maxwell equation, is equal to curl of B, Ampere's law. Okay. So, these two can be combined easily. So, I take a curl here 4 pi by c curl of j equal to curl of B. Okay. So, we have come up to this far. Then the right hand side is we know that this is gradient and of divergence B, grad div B minus del square B. Okay. So, this is of course something we know from our vector algebra, and from Maxwell equation we also know that divergence B is 0. So, we can just write this as minus del square B. Okay. Now, we know that curl of J is minus ns square ns E square by m c. So, just multiply both sides by 4 pi by c and see what happens. Minus ns E square by m c into 4 pi by c, right, into B is then this. So, that means del square B equal to 4 pi n s E square by m c square into B, and that is this equation. This so, that is the equation that we have to now understand. So, this is an equation that follows trivially from but just by doing 2 more steps and using Maxwell equation starting from London equation. Okay. So, what does this say? Suppose you are in one dimension. Okay. So, then this equation tells you that okay. So, let me just draw this geometry. So, suppose you have this is called a semi-infinite superconductor on this side. So, the x equal to 0 onwards, right hand side is superconductor and left hand side is vacuum. I mean, there is no superconductor here, is vacuum say. And then you are putting a magnetic field here B 0 which is at x equal to 0 and left of it you have applied we have applied a magnetic field. Then what one would like to see is how B behaves with x, and beyond x equal to 0 of course, it enters the superconductor. So, it has supposed to enter the superconductor, and one can write down this equation along only the B that direction. So, that is del 2 B del x 2 equal to 4 pi n s e square by m c square into B, which is conventionally defined as 1 by lambda square B. Why is it defined as this? You can immediately see from 2 sides of this equation, this part of the equation, that this quantity has the dimension of 1 over length square. So, that means I can define a length lambda which is such that 1 by lambda square is this quantity. So, lambda square equal to m c square divided by 4 pi n s e square. So, that is a length scale that I obtained from this calculation. So, this length scale appears naturally from this equation, a combination of London equation and Maxwell equation. So, this the solution to this is trivial. We know what the solution is. The solution is B x, suppose B starts from here, B naught is here, then let me just draw it in a different ink. So, B naught has a value, constant value on this side. So, this is B naught, and then this side is non superconducting vacuum and this side is superconducting. So, B naught has a value which is this, and so let me wipe this out. So, this side is completely superconducting and that is my B naught value, and so B naught has a solution which has to decay. So, what is the solution? B naught B of x equal to B naught e to the power minus x by lambda, right. So, that has to be the solution of this equation, and that is it starts from B naught and then decays. So, within a length scale of lambda it becomes nearly 1/3 of the value, and this lambda is typically depends on the system of course, within some hundreds and thousands or thousands of angstrom it decays down to almost 0. So, that means if you go inside the bulk of the superconductor, then there is absolutely no field. You will not see any field, no matter how you cool, what you do, it does not matter. This is the equation, and this tells you that there is no choice, that the magnetic field has to fall down to 0 within inside the superconductor. Okay. It almost vanishes by a certain distance. So, this basically explains the Meissner effect. So, this is in a way Meissner effect, except that at this it also tells us that at the surface of course, you will have some region typically of length lambda, over which you will have a magnetic penetration only at the surface, but beyond that there is no magnetic field inside the superconductor. So, this was the way magnetic field going to 0, perfect diamagnetism was explained by London's equation. Okay. And it also predicted this length scale, that there is a length scale over which this will happen, and it came out naturally from look at this only thing that depends on the system here is this ns. So, it just in this equation at least is the dependence is only through the conduction density of the superconducting fraction. So, that is what a so, for example, at extremely low temperature where the ns is almost equal to n, you can figure out what your lambda is and compare with experiments to check the validity of it, and indeed this has been done and checked that this is what happens in a superconductor. The other interesting thing that I was mentioning was that the existence of a supercurrent. Now, that is actually very easily shown if you for example, take a ring, okay, and thread a magnetic field through the ring. So, suppose I have a ring like this which is superconducting and thread a magnetic field. Perpendicular to the ring, through the ring, and there is a there is supposed to be a current I. Okay. So, how do I find that? So, this for example, suppose this flux is phi. So, phi equal to B dot ds. So, this is to be integrated over this surface, and ds is a surface normal to B, and so on and so forth. This you know already. So, surface element normal to the plane of this ring, for example. Okay. Now, we also use this equation curl of E is equal to minus 1 by C del B del T. Okay. This we have been using consistently. So, so then curl of E dot. So, let us just put it here. So, let us just start from this equation and write del phi del t. Okay. And so, 1 by C del phi del t minus 1 by C del phi del t is minus del B del t 1 by C into ds. Okay. Now, 1 by C del B del t is this. So, this will become curl E dot ds. Okay. Now, this using Stokes theorem we can write as E dot dr, where r is a line element that over a contour which is enclosing the surface S. Okay. So, what we can do is to choose choose this line element, the line over which we are integrating, just choose it inside here, take the line inside the superconductor. So, that is the contour over which you will do the integration. And we know that inside the superconductor E is 0. So, this will lead to 0. That means, d phi dt, the change of flux is 0. So, that means what? That means that suppose now I switch off the magnetic field. So, magnetic field is externally applied, I can switch it off from outside. So, we do that. So, this magnetic field is switched off now, but then this equation tells us that the flux remains constant. So, flux has to be whatever it was before before B was switched off. So, this area times B is the flux, and that has to remain constant. So, that means that there has to be a current that keeps on flowing to generate this flux, to keep the flux at what it is when I put the magnetic field, right. So, so this is kind of interesting. This means that supposing you have a superconducting ring and you are you have put a magnetic field, and so this is the geometry. In a ring you put a magnetic field, you have a flux. So, flux is created by the B field that is applied from outside. Now, from simple Maxwell equation and the fact that the electric field inside the superconductor is 0, I can show easily, and what I did was to show that the flux has to remain constant. It is also the other way around. So, suppose I started with a flux which is 0 and I wanted to put a magnetic field, then the flux will keep remaining 0 because there is this there will be a current generated that will try to keep the flux as it is. So, how does one do this experiment? You can just take the ring, superconducting ring, take it above its take it above its transition temperature, put the field so that there is a field inside. So, there is a flux passing through the through this ring. Okay. So, once that is set up, then start cooling, and you cooled it below superconducting transition temperature. So, the ring becomes a superconductor. And now what you do is that you simply try to withdraw the field, and you can, of course, you can switch off the source of the field from outside. And what it will do, the superconductor, is to have a supercurrent which will keep on flowing through this, so that the field remains constant whatever it was the same value, and that is called a persistent current, a supercurrent. And that since the flux has to be constant, the current has to also remain constant. So, it is a dissipationless current that flows in the superconductor, and it just keeps on flowing because no change in flux is allowed, and that is exactly what happens. And that is what I mentioned in the earlier in the lecture, that the one of the ways to see that there is you are in a superconducting state is also to see that there is a supercurrent, and one can actually. So, how do you know there is a supercurrent? You can actually measure the flux and see that the flux is not decaying. So, therefore, one can actually do this experiment, and one finds that this flux is not only constant, it is a constant over an enormously long time. People have done these experiments for days, for months, for years, and kept it on and tried to find any decay in the supercurrent, and so far the estimates are that this supercurrent will not decay, and decay time is probably is indeed more than the life of the age of the universe itself so far, which is about 13.7 billion years, and it is certainly more than that. If the material has very little defects, and it is a pure good material, superconductor, is almost absolutely no decay of the current in a very pure superconductor without any perturbation, of course. As I said, it has to be a pure material, superconducting material, where you set up this supercurrent and measure the supercurrent or the flux year after year, you will find absolutely no decay in the superconducting supercurrent in it. So, that is another way of seeing that something is a superconductor, but of course, much easier is to see that it is a diamagnet, but these are all evidences that you are in a very different new state, and that state is something that one has to understand. And so, that understanding came from a remarkable theory, and this theory was proposed first by Bardeen, Cooper and Schrieffer, and they later on got Nobel Prize for it. But it has a long history. Almost every big physicist, every famous physicist that you know of, starting even from Einstein, Niels Bohr, Heisenberg, many of them tried their hand on a theory of superconductivity. And although it was realized that superconducting mechanism involves the lattice vibrations, because remember that isotope effect, Tc goes as 1 over root m, that told us already that the lattice vibrations are the frequency of the vibration goes as 1 over root m, and that is involved in, that has to be involved in the mechanism that gives rise to superconductivity. The main difficulty is of course that electrons are all the electrons are negatively charged. So, they will repel each other, right, and it was realized that at least people thought about it, that the superconductivity is a state where you have a condensate, it is like a Bose condensate, and so therefore, you need to pair up electrons, and you need an attractive interaction for that to happen. And now of course, we know that indeed there are these so called Cooper pairs, 2 electrons form a pair, a bound state, which we call Cooper pair, which is responsible for superconductivity in a otherwise repulsive Fermi gas, right, Fermi system. So, that is a theory, that is where the theory of superconductivity starts from, and that is something that we will carry on doing from now on. So, so the phenomenology is now established, that you have a Meissner effect, you have zero resistivity, and both of them are required for you to have to define something as superconductor. And there is this London equation, which is a phenomenological equation, but that shows how magnetic field decays inside a superconductor, leading to Meissner effect. And then of course, there are these experimental evidences that tell us that there is a and of course, there is this persistent current, which I just showed, and then there are remember, all these are phenomenological theories. So, so far we have not done any microscopic theory, not started from underlying basic interactions in the superconductor to produce a superconducting state, and that is the task that as I said, many people tried, and finally Bardeen, Cooper and Schrieffer achieved in 1950s. Now, that theory requires to understand how the electrons attract each other, and that attraction has to lead to form a bound state of 2 electrons, and that will lead to a sort of condensate state, which is where the resistivity vanishes. All the phenomenology that I described has to come out of such a theory, and that is exactly what BCS theory does, and that is what we will start in our next class.